Bridges versus earthquakes. Bridges are particularly vulnerable to earthquake damage, especially older ones, and engineers are developing innovative designs and techniques to enhance their seismic resilience, including hybrid sliding rocking columns and earthquake-resistant materials. Ground shaking. Earthquakes cause ground shaking, which can lead to structural damage in bridges, including cracks in concrete and damage to piers and abutments. Fault ruptures. Bridges crossing fault lines are particularly at risk, as ground movement during an earthquake can cause significant damage. Soil liquefaction. In areas with saturated soil, earthquakes can cause the ground to behave like a liquid, leading to settlement and damage to bridge foundations. Tsunamis. Earthquakes can trigger tsunamis, which can cause extensive damage to coastal bridges and infrastructure. Hybrid sliding rocking, HSR, columns. These columns are designed to allow controlled movement and rocking during an earthquake, preventing damage to the columns themselves. Seismic isolation, using isolation bearings or other systems to decouple the bridge from the ground, allowing it to move independently during an earthquake. Damping systems, installing dampers, such as viscous or tuned mass dampers, to absorb seismic energy and reduce vibrations. Ductile materials, using materials that can deform and absorb energy during an earthquake, such as steel and reinforced concrete. Reinforced concrete, using steel to reinforce concrete, making it more ductile and able to withstand bending forces. Retrofitting, strengthening existing bridges to improve their seismic performance. Advanced materials, using shock-absorbing asphalt, geosynthetics, and fiber-reinforced polymers, FRP, to help roads and bridges withstand seismic shocks. How bridges are designed to withstand earthquake. Bridges are designed to withstand earthquakes through various techniques, including using flexible bearings for base isolation, incorporating ductile materials, and employing damping systems to absorb seismic energy. Base isolation. This technique separates the horizontal movement of the foundation from the rest of the structure using flexible bearings. Ductility and material section. Earthquake-resistant designs incorporate ductility, which is the ability of a structure to bend, sway, and deform without collapsing. Damping systems. Damping systems are used to mitigate the effects of vibrations, including those caused by earthquakes. Reinforced concrete construction. Using reinforced concrete construction techniques can help to enhance the strength and stability of the bridge. Symmetry and regularity. Symmetric and regular bridge designs can help to distribute forces more evenly during an earthquake. Earthquake shock absorber. Earthquake shock absorbers, also known as seismic dampers or fluid viscous dampers, are devices that dissipate the kinetic energy of seismic events, reducing the impact on structures during earthquakes by converting energy into heat. Hydraulic devices. These dampers are essentially hydraulic devices, similar to car shock absorbers, with a piston inside a cylinder filled with a viscous fluid, like silicone oil. Energy dissipation. During an earthquake, the building's movement causes the piston to move within the cylinder, forcing the fluid to flow, which dissipates the energy as heat. Placement. They are strategically placed within a building, often between columns and beams at different levels, to effectively regulate and minimize building sway during earthquakes. Seismic dampers are used in damping the oscillations of a building during an earthquake. Earthquake-proof bridges. Earthquake-resistant bridge designs focus on incorporating ductility and flexibility to absorb seismic energy, using materials like steel and incorporating features like hybrid sliding rocking columns or dampers to minimize damage and ensure bridge functionality after an earthquake. Bridges are designed to be flexible to allow them to move and sway with the ground during an earthquake, rather than being rigid and prone to cracking or collapse. Large pendulums or other damping systems can be incorporated into bridge towers to absorb seismic energy and reduce vibrations. These are areas designed to allow controlled yielding and deformation during an earthquake, absorbing energy and preventing catastrophic failure. Using materials with high ductility, such as steel, and reinforcing concrete with steel bars can enhance earthquake resistance. Researchers are exploring the use of smart materials, like shape memory alloys, to create more resilient and self-repairing bridge structures. Thank you.